Okay, hello everyone. It's Paul Drabble, Senior Marketing Manager with Delta Q Technologies, part of the Zappi group of companies. So we're well into day 2 of the Future of Electrification virtual conference. So welcome and thank you all for tuning into this session topic, the evolution and future of battery charging technology. All sessions are being recorded, so they're available to watch on demand for everyone's convenience in the future. Questions from the audience really enhance the value of the session, so we encourage you to share your thoughts in the Q&A tab in the top right of the session window, and I'll bring up those questions to discuss at the end of the session. And please note that your questions will be posted privately. With that, it's my pleasure to introduce Chris Botting, who is the Manager of Research Engineering at Delta Q Technologies. And Chris, I will hand the session control over to you now.
Great. Thank you, Paul. So, as Paul said, we'll be talking about where we are and where we're going with battery charging technology. So, in terms of the outline today, I'm actually going to start by looking back to where we've been in some of the trends over the past decades, particularly focused on the golf cart industry. Then we'll look at the impact of lithium ion, which has really caused major changes in the charging industry and the EV industry as a whole. And then that drives the need for higher power and higher power density. So we'll talk about that need, how it will be met, and what that means for future charging trends. Overall, hopefully by the end, we will have identified the big picture battery charger trends, both past and future. And I'm hoping that you leave with some information that can help you to anticipate the changes coming to your applications. So let's start by looking back. Golf carts is a market that Delta Q has been in for almost 20 years. So we know it very well. We work closely with the major vehicle OEMs and with the battery makers. But the trends that I'm going to talk through are also present in many other industries. They could equally apply to industries like forklift, for instance. So as you can see, there's been quite a bit of change. If we start by going back to the 1960s, really through the 1990s, there's about 3 decades there that battery charger technology did not change much. And you can tell it really just by looking at the chargers. So chargers operated at the line frequency, at the AC line frequency of 50 or 60 hertz. They were typically ferroresonant or SCR based, that silicon controlled rectifier. But the main feature really is what you see there in the middle of that open charger, which is that inside of that bent sheet metal box, the charger is largely a big transformer, a big heavy transformer. Because it's operating at 60 hertz, it ends up being at least 10 kilograms of steel and copper, which is a major size, weight. It has fairly poor efficiency and poor power factor. As a result of all of that, these chargers were unsealed and were really not suitable to be on board. The one saving grace, if you can call it that, is that they were repairable, which raises the question, wouldn't it be better to have something that doesn't break? But that's where we started from. So moving forward to the 2000s, this is when Delta Q enters the market with high frequency or switch mode power supplies. So switch mode power supplies changed the paradigm. What you're seeing in the upper right is the quick charger, our first product, and one of the first high frequency switch mode power supplies in the industry. And what this effectively does is, rather than using the line frequency, the 60 hertz, you use semiconductor switches to do power conversion at a higher switching frequency, typically 60 kilohertz. So the increase is 1,000 times or 3 orders of magnitude. And the key thing to understand here is that as the frequency increases, the transformers and the inductors and the capacitors get smaller. So it doesn't scale up directly. The transformer didn't get 1,000 times smaller, but it did get 30 times, roughly 30 times smaller and lighter. That's the pale yellow box that you're seeing, the pale yellow rectangle that you're seeing in the left rear of that cut open view of a quick charger. This is now a two-stage charger where the input is power factor corrected, and it's high efficiency. The efficiency, losses were roughly cut in half. All of that also adds up to having a charger which can now be sealed, is much smaller and lighter and can be sealed because you're generating a lot less waste heat in the charger. The heat can now be conducted away to the heat sink, which is the black fins that you see on the right and the left of the charger there. Also, as a bonus, now that this is a digitally controlled product with a microcontroller running software, you can now have complex charge profiles and more precise control of the charge and use your interfaces and features. So moving into the next decade, into the 2010s, the change here is not so much in the power electronics technology, but in terms of how it's packaged. In particular, a focus on DFM, or design for manufacturing. So what you're seeing there in the upper right is our IC650 charger, which was our first charger launched in 2013, 10 years ago. The first charger in this space to be not just sealed, but much more rugged to shock and vibration. So as you can see from the photo, the assembly photo there, you've now got a single circuit board. All the components are surface mount. Those are those larger black rectangles that you're seeing on the top of the board on the two sides there. Those are the semiconductor switches and diodes. They're no longer through-hole devices clamped with screws and stainless steel clamps. They're now surface mount and cooled through the board through thermal vias. The enclosure is no longer multiple pieces that have to be screwed together. It's now a single die-cast aluminum housing, which makes it more robust and takes some of the manufacturing and the assembly out of it. It also means that we can have a custom shape to the inside of that casting, so that all of the tall components, all the bulky components like the transformers and inductors, which have been shrunk down but are still there, they can fit the skyline of that PCBA can fit into the skyline of that casting like fingers in a glove. So from a mechanical design point of view, this becomes much simpler, and also because you can now use thermal glue or potting with silicone-based potting, which is shock absorbing and thermally conductive. You can now hold those components rigidly on both sides, to the circuit board on one side, to the casting on the other, and you also have the heat path there for cooling. So it's now much more robust to shock and vibration and to drop onto concrete surfaces. Also sealed better. There's less openings to seal. There's a single case, a single flat interface to the lid, which is not shown. And so that all adds up to the charger now being fully suitable to be on board in a way that the earlier chargers, particularly back in the line frequency days, were not. Added features here also include CAN bus communication, USB host with a USB stick, data logging, and user display, which you can see in the upper right photo. So that takes us up to this decade. And really the big shift here in golf was the move to lithium ion. So I've been talking about changes in the charger technology. Now I'm talking about a change in the battery technology. And the reason is that this will then have a direct impact on charger technology and really on every aspect of the industry. So the first mover in golf was E-Z-GO. They introduced a lithium ion option in 2017. And it's been wildly successful, such that they have actually now phased out lead acid batteries in the last year or so in many of their vehicles. Club Car followed a couple of years later with a lithium option. Yamaha later still with a lithium option. And benefits here are, of course, the battery is much lighter, which has an impact on range. And also, in the case of golf, is helpful because it will reduce the wear and tear on the greens. The batteries can charge faster, but in particular, they have longer life and longer warranty. Warranty being one of the key differentiators in the golf market. And also more energy efficient, so power bills go down, and zero maintenance. If you have a fleet of flooded lead acid golf cars, they tend to need watering on a regular basis and also washing. So what you're seeing on the right there, these are both views of the battery pack, which sits under the seat of a golf car. You just flip the seat up. What you're seeing on the right is the E-Z-GO battery, which is a NCA lithium pack from Samsung SDI. On the left, what you're seeing is a lead acid pack. Actually, this is a sealed lead acid pack, such as what Yamaha is offering. AGM being a type of sealed lead acid. And this is actually interesting because AGM sort of offers a poor man's lithium in that you can get some of the lithium benefit at a fraction of the lithium cost premium. It's not lighter, but it may have longer life. It'd certainly be more energy efficient with an efficiency somewhere between flooded lead acid and lithium ion. Flooded lead acid being typically 80% round trip efficient. AGM maybe 85%, but then lithium is like 90 or 95%. So some of the benefit, and also being a sealed battery, there's no maintenance, there's no watering. So let's pause here for a moment to talk more about the impact of lithium ion, because this is really a game changer. You've seen many charts like these, I'm sure. The charts with lithium ion showing how it's improved over time tend to either look like the chart on the left where things are decreasing, that's usually cost, or on the right where things are increasing, which is usually, density or manufacturing volume and investment or vehicle range. The two charts that I've shown here, that I've chosen to show here, really focus on, I think, the reasons from a vehicle point of view that we're really seeing lithium move into these markets. So lithium ion on the left, what you're seeing is cost at the pack level. So lithium ion has come down tremendously, almost by a factor of 10 in the last 12 years or so, and it's continuing to drop. And it has almost reached cost parity with lead acid. Of course, that's going to depend on the industry and the application. But the red line that I've shown there with lead acid around $100 US per kilowatt hour, it's a range, obviously, but you can see from those green lines that it's coming very close down to the pack level, maybe $150 per kilowatt hour at high volumes. At low volumes and in the aftermarket, of course, you'll be paying more. If you look closely, you'll actually notice that the cost declines have stalled in the last couple of years. There's actually a note there showing a 7% increase in 2022. And that is due to supply chain disruptions, and in particular, the exploding demand for some of the key inputs, the metals and the minerals, like lithium and cobalt in particular. But I think that these, as the manufacturing and the mining scales up, these things are going to sort out, and cost is going to continue to keep coming down, but at a more moderate rate. What you're seeing on the right is exciting, because this is energy density on a volume basis. Now, often you see energy density shown on a weight basis, so watt hours per kilogram, and that is important. But in many of the applications that we serve, energy density on a volume basis, watt hours per liter, is actually more critical. There are certainly applications where low weight is desired, like power sports and electric motorcycles, e-bikes and scooters. In some applications, weight is even a feature. In forklifts, where the weight of the battery is used as a counterbalance, and as people move from lead to lithium, they may actually add lead weight to make up for the lost weight. But the energy density that you're seeing there, some of that growth is due to improvements in the chemistry, where the capacity and the voltage have been increased, where they've been able to reduce space used by non-active material in the cells. But most of that growth is actually not about the cells. It's about packing the cells into a battery box better. So building cells into modules, modules into packs, or sometimes cells directly into packs, and taking the place of structural elements, being able to simplify. So again, I've shown a line for the rough range of where lead acid is, and you can see that at a pack level, lithium ion at first did not actually exceed the density of lead acid because of how inefficient the pack designs were, how much empty airspace there was. That has definitely changed in the last decade, and now it's leaps and bounds. So both the cost curve and the energy density curve, these are really learning curves as the manufacturing volume ramps up, and as the OEMs gain experience. And these are trends which are going to continue. So the other thing about lithium that really impacts charging is that lithium can charge much faster than lead, and I don't think that this can be overstated. So with flooded lead acid in a deep cycle application, it is difficult to charge faster than about 8 hours if you're doing a complete charge. What you're seeing there at the bottom is some data from my lab, where I've taken a 48 volt flooded lead acid golf pack. I've discharged it to 80% depth of discharge, and I'm charging it with a standard 3-stage or IUI charge profile. 3-stage, you can see from the plot on the right that the first stage is full constant current or constant power, so the bulk phase. Then there's a constant voltage, so power tapers down as the current tapers down. And then finally, the third stage is called finish, and that's a lower constant current. I've charged here with a range of powers from 650 watts to 1500 watts. And then I've actually lined these up not with the same starting time, but with the same ending time. So what that shows there on the right is that as the bulk time decreases, as you have higher power, so you spend less time in the full power bulk, you still tend to spend just as much time in constant voltage absorption, and in particular in that low constant current finish phase. That just takes a certain amount of time. And on the left, you can see those same points, charge time plotted versus power, and you can see it's approaching about 8 hours. So what this really shows is you could put a 3 kilowatt, a 10 kilowatt battery, a charger on this battery, and if you don't change the charge profile, it's not really going to be able to get below a minimum 8-hour charge time with this battery fully discharged. Now, with sealed lead acid, particularly with thin plate pure lead AGM, with those thin plates give it higher surface area, so it has higher power and higher charge acceptance. Those can be charged at higher rates, and maybe it's possible to get this down to 4 hours or so. But that'll still depend on the charge profile and what you end up doing at end of charge. And this is really baked into the chemistry of lead acid batteries, that particularly when they're used in a deep cycle application, in a traction application, they need to have 10% more amp hours put in than are taken out. So they need a charge return factor of about 110%. With flooded, maybe 105% or so with sealed batteries. And that finish current, that extra 5 or 10% charge return is what you're seeing in that finish phase. And it happens slowly because you're pushing above the gassing voltage. So this could be sped up by increasing the current. You could increase the voltage in the constant voltage absorption phase. You could increase the current in the constant current finish phase. You could decrease the amount of charge return, but these would have detrimental impacts on battery life. They'd very much be trade-offs. As you push the current and the voltage higher above the gassing voltage, you'll gas more vigorously, you'll generate more heat, the battery will lose more water. And if you decrease the charge return factor below that 110% that a flooded battery needs, you don't fully convert all the lead sulfate, and you can have permanent loss of capacity and shortened battery life. So really, it's possible to charge lead acid faster, but there are definitely diminishing returns with what's achievable in terms of maintenance and battery life. Lithium is an entirely different story. I have similar charge plots for lithium, which I did not show because they are much less interesting. And essentially, if you double the charger power, you really can almost cut charge time in half. Whereas if you double charger power with lead acid, maybe you're cutting charge time by 25%. So with most lithium batteries, charging in one hour is generally easily achievable, sometimes less. This really comes down to the battery construction and the BMS, but in particular, whether there's enough copper and low resistance in the charge path, in the cables, the connectors, the terminals, the internal bus bars, and the tabs in the cells. But from an electrochemistry point of view, there's no inherent limit to charge time the way there is with lead acid. So what does this mean? What it means is that battery charge acceptance is no longer the bottleneck. So thinking back to those past generations of charger technologies, the charger was improving, but the battery was not. The charger could get smaller and more rugged and robust. It could move on board, it could be sealed, but the battery was still really the limit. And now with the shift to lithium ion, the battery is no longer the bottleneck. So that means that the charger has to keep up. Charge rates need to keep up with the battery. So if we add this up, those first plots of lithium ion capability showed that there's increasingly low cost and high density. So you can pack more battery into a space and it costs less. And the result is people start using larger batteries. Not always. In the golf market, the move has actually been to smaller batteries for cost reasons. Previously, the lead acid batteries were oversized, sized so that they could meet their mission of a certain number of rounds of golf at end of life. And since lithium batteries have less degradation and a more unpredictable degradation of capacity over time, they didn't need to be oversized to the same extent. So it was actually possible to put smaller batteries in for cost reasons. But generally, the long-term trend is going to be to bigger batteries. So if you have bigger batteries and those batteries can be charged at higher rates, much higher rates, then that's going to drive toward much bigger chargers. And again, not always, depending on the application. The first movers in golf not only moved to smaller lithium batteries, but they actually moved to lower power chargers because they could, with a lower charge return factor, lithium just needing to put in a charge return of about 100%, 101%, and not needing to put in that extra 10% at a low current. It's possible to charge lithium at full power for almost the entire charge. So even with the same charger power and the same battery size, charge times come down. And in this particular application, the first uses was smaller batteries and smaller chargers for cost reasons. But in a lot of applications, they're going to take advantage of the bigger batteries and the faster charging, which can come with it. So that moves the bottleneck. So what's the next bottleneck? It's going to be all around the charger. The AC supply to the charger. Where can you plug in and get enough power? The DC current out of the charger. How do you carry all that current without generating too much heat? And then finally, the onboard charger size. How do you pack a bigger charger onto a vehicle? So let's take those one by one. First, the AC supply as a bottleneck. So as I said, the power that you need is going to determine where you can plug in. And the solution here generally is going to be that you're going to need to increase voltage and current and number of phases by plugging in different places. So there are certain standard power levels that tend to pop up a lot in the charging industry, and those power levels there's nothing magic about them. They're just really based on how much power can you get from certain outlets and certain breakers. So starting in North America with a residential outlet at 120 volts at the bottom of that arrow, what you're looking at is a 15 amp, a standard 15 amp breaker. The electrical code lets you draw 80% of that continuously, so 12 amps, 120 volts. Your input power is about 1.4 kilowatts, but then you take into account losses in the charger, which is about 90% efficient, and also sag in the AC line, and you're looking at about a 1.2 kilowatt maximum charge power. And by not a coincidence, many of our chargers are 1.2 kilowatts for that reason, so they can take full advantage of a dedicated 120 volt circuit in North America. In Europe, they're in better shape because the voltage is higher. So the standard outlet there, 230 volts, 10 amps. So you've got over 2 kilowatts of input power. And then again, taking into account losses, you end up with roughly a 2 kilowatt maximum charger output power. If you need more power than this, you now have to move beyond residential outlets, which means that you need to think more carefully about where you're going to be plugging in, and you may be calling an electrician when you're planning a facility. So on the top are the EVSEs, electric vehicle supply equipment, or charge stations, as they're called, the North American single-phase plug and the European three-phase plug. And on the bottom, we have the industrial plugs. There's a wide range of them in North America. I've shown a couple standard common single-phase and three-phase plugs with the straight blades. And in Europe, they have these connectors. The blue is single-phase, the red is three-phase, which are commonly used in a industrial setting. So you'll often see chargers that are 3.3 kilowatt, 6.6 kilowatt, and 10 kilowatt if they're talking about the output ratings. Marketing folks like to talk about the input ratings, which are a little bit higher. So, 3.6, 7.2, and 11. But those all basically mean drawing 16 amp or 32 amps from a 230 volt line for 3.3 or 6.6 kilowatts. In some cases, drawing 48 amps from a 60 amp breaker on a 230 volt single phase line to get 10 kilowatts. And then beyond that, you need to move on to three phase power, where 16 amp three phase, 32 amp three phase brings you up to 10 kilowatts and 20 kilowatts. And of course, if you need more power than this, it becomes increasingly complicated figuring out how to plug in, and the standard connectors are not necessarily going to help you. So that's the input, where the solution is increase the voltage, increase the current, and increase the number of phases. And there's a similar problem with the DC output. DC current is also a bottleneck, because the DC current from the charger passing into the battery has conduction loss. So all the resistances in the cables and the connectors and the bus bars in between and in the battery pack itself. DC current heats the battery, heats the cables, heats the connectors, and its heating is proportional to the square of current. So things run away pretty quickly as you increase current. This is also true when you're driving the vehicle, the continuous and the peak traction currents. Not usually a problem for smaller onboard chargers. This is really more of a problem when you start looking to do offboard DC fast charging at very high rates. You can add more copper to decrease the resistances, but there are limits to this, practically speaking. You're adding cost, copper is expensive. You're also adding weight. And so there is a practical limit around a few hundred amps where it's simply not practical to add more copper. You can add cooling, but there are also limits to how quickly you can extract heat from the battery and the charger. And we've even reached the point in the last few years where the offboard DC fast chargers for automotive EVs, as they've pushed up from 150 kilowatts to 350 kilowatts, they've started having to liquid cool the cable and the fast charge connector, not just so it doesn't overheat, but also so that they don't have to add so much copper that it becomes difficult for some users to pick up and plug in, and has a bend radius which is awkward to deal with. So from a practical point of view, throwing more copper at the problem has limits, and throwing more cooling at the problem has limits. And so the solution has to be to increase DC voltage. So what you see here is a map of common voltages, and there are reasons for those common voltages. I've shifted from golf to a different industry. Those compact excavators are all publicly available products or announced products that I've found online, which are shown to be at those voltages. 24 volts in scissor lifts and class 3 forklifts is a common old voltage with lead acid. 48 volts is what golf cars use, but it's also being used for the smallest compact excavators. 48 volts is a key voltage because it's the highest nominal battery voltage you can use and still keep your maximum charge voltage below 60 volts. And 60 volts is a critical number globally for what is considered to be legally touch safe in some jurisdictions. So some manufacturers want to keep the voltage as high as they can, just below 60 volts. 80 volts, also a traditional lead acid voltage used in the largest class 1 forklifts. But with lithium ion, typically you're moving up to 96 volts or 100 volts. Both of those, the 80 volt lead acid and the 100 volt lithium, are built around keeping the charge voltage below 120 volts, which is sort of the next step up in what is considered to be hazardous voltage. Beyond that, for a variety of reasons, including the availability of parts and semiconductors. You move up to 400 volts, typically about 360 volts nominal. This is the voltage that is commonly in automotive EVs, and this hardware is being adopted in industrial markets. And then if you need more power, then some are just leapfrogging straight to about 700 or 800 volt nominal, which is also where the automotive EV space seems to be headed. So again, the solution to current too high is to increase DC voltage. And what you end up with actually is that at all of these different voltage levels, the currents tend to be similar. The peak and the continuous currents tend to be similar. They just increase voltage as more power is needed. When you need to drive at highway speeds, or you need to replace a high-powered diesel engine, or you need to be able to DC fast charge at a high rate. So that's the input and the output of the charger, and now there's the charger itself. So customers are demanding more power in the same onboard volume. Of course, customers want, and why not, more power in less space. As an example here, these are a couple of chargers from the automotive EV industry that I've opened up, a couple from Volkswagen. The one on the left is 3.3 kilowatts. The one on the right is 6.6 kilowatts. And as you can see, they look almost exactly the same. They are, in fact, the same dimensions, the same bolt pattern. They've shuffled around some connectors, but for all intents and purposes, this is twice the power in the same box. So how do you do that? How can power density be increased? I'm not going to tell you how they did it with this charger, although I have opened them up, and I will actually show that at the end of the presentation. But let's start by looking at the answer to that question. What are the ways we can shrink chargers, increase power in less space? Well, at a high level, there are a few things you can do. You can try to increase efficiency further, and that will decrease the amount of space that you need to spend on cooling. At lower powers, that's decreasing heat sinks and fans. At higher powers, maybe that's decreasing the size of your liquid cooling channels. But there are limits to this. You can further increase switching frequency and try to get even further reductions in the size of the magnetic components. This is actually moving in the opposite direction of efficiency. As you increase switching frequency, you tend to increase losses. And that means that you need better cooling. So better cooling, closer coupling of the heat generating components to the cooling. These are ways to get smaller. Finally, denser construction, which may sound obvious, but if you can pack more components in less space with less air, that's really ultimately what we're trying to do. And there are ways of doing that. And then rounding things out, sort of cheating, system integration is if you can't reduce the size of the charger, if you can't reduce the size of this box, maybe you can combine it with another box. If you got a separate box that's performing some other function, why not put those, two boxes together, and you can reduce the overall system size and cost and increase density of the system. Offboard charger, this is a similar move. So more system integration for the functions to manage an offboard charger, but also ultimately, if you can't get the box small enough on board, you may have to move it offboard. So let's start with the efficiency. The good news is that as you increase efficiency, you can reduce size and cost up to a point. So it can be win-win-win. A little bit of a busy schematic here, but what I'm trying to show is that the cost versus density curve almost looks like a bathtub, where there's a downward slope. The bottom where you settle to a minimum point, and then you start climbing the other side of the bathtub as the efficiency increases further. So where we started back with those line frequency chargers was up at the left, where you would high cost, large heat sink size. Think of all of that copper and steel that was present in the charger so that it could shed heat. The semiconductors weren't a big part of the cost. And as we moved to switch mode power supplies, we added to the semiconductor cost, we reduced the raw material cost, all the aluminum and steel, and the net result was that things got smaller and things got cheaper and the efficiency increased. And that's the good news. The bad news is that you are here. This is basically where we are now. We've already picked all the low-hanging fruit. And although that sweet spot is slowly moving forward to higher efficiency and higher density as semiconductor technology slowly evolves, from this point, pushing up to higher efficiency tends to increase cost. Pushing up into higher efficiency, there's diminishing returns. You need more cost in the electronics, and it's not fully offset by the cost reductions in the packaging and the case. So what can we do? And in fact, what are we doing? Soft switching is one thing. So the first generations of high frequency power supplies had hard switching, which means basically that there's overlap between the voltage and the current. You typically want to be switching when either the voltage or the current are zero. And if there's overlap, as shown in those shaded gray areas, that's where the losses occur. And that's a loss which has occurred with each switching instance. You generate heat there. Maybe just as importantly, you also generate noise, electromagnetic noise, which then has to be filtered, which adds size, weight, and cost with filter components. So this is proportional to frequency. If you have more switching instances, you have more losses and more EMI. And so if you double the switching frequency, you double those losses. One solution to this is resonant converters, where there's a natural commutation where a resonant tank forces current to pass through zero, and the current, which is sloshing around in your converter at this natural resonant frequency, lets you soft switch. So switch when the voltage and the current aren't overlapping. So this is also a trend which was present in the 2010s and is something that we implemented starting with our IC650 charger there. The output DC-DC converter is what's called a LLC, inductor capacitor. Those are the main elements in the resonant tank. The AC-DC converter at the input is still hard switched, but this partial solution has let us further increase switching frequencies up to about 200 kilohertz and has reduced losses and EMI. The other thing that you can try to do is lose the diodes. So the idea here is that diodes have fixed losses when they rectify AC to DC. You have a fixed forward voltage drop across a diode, and so loss is proportional to the current across that say 0.7, 0.8 volt drop. You can replace diodes with switches, which is called active rectification. And if you choose switches that have a low enough resistance when they're on, then the result is greatly decreased losses. But this adds cost and complexity. So conventional switch mode power supplies have diodes at the input and the output. So the opportunity where this makes sense is when you have low voltage and high currents. So at the input, that tends to mean in Japan and North America with 100 volts and 120 volts. You can do things like bridgeless input, which means that you've gotten rid of the AC-DC converter's diode bridge rectifier. And at the DC output, similarly, there's something called synchronous rectification, which means that you have diodes. You replace the diodes with switches that are switching synchronous with the current. So they switch only when the diodes would have conducted. This again makes sense mostly at low voltages like 12 volts, 24 volts, maybe 48. But if you think back to those previous slides where we looked at how increasing power means that the AC voltage increases and the DC voltage increases, then you can see that these opportunities are going to make less and less sense as you move to higher power. As the AC input voltage is higher, as the DC output voltage is higher, there are diminishing returns, and it may not make sense to replace diodes with switches. So faster switching, as I said, we had previously increased the switching frequency by a factor of 1,000. Why can't we just keep doing that? And to some extent, we can, but today, where we're operating around 100 kilohertz is really the practical limit with the conventional silicon MOSFETs. With the resonant converters that we talked about earlier, it's possible to go a little bit higher, and we have. But if you want to go up to 1 megahertz and try to further reduce the size of your magnetics, you need to use what are called wide bandgap devices, gallium nitride and silicon carbide. These have much lower switching losses, so you can increase the switching frequency. The trade-off is that traditionally these have cost more, although that's changing. Traditionally, the reliability was not as known because they were new to the market. That's also changing. What's changing a bit more slowly is that this can cause issues with second sourcing. So particularly during the last couple of years, it's been very clear with supply chain disruptions that it's important to be able to have multiple manufacturers who can provide interchangeable parts. And if you use standard industry formats like the gallium nitride switch shown on the top with the 3 leads, then it's easier to swap parts between manufacturers. But the GaN and the SiC, but particularly the GaN makers, are tending to use smaller custom packages, which have lower inductance, can let you take full advantage of the switching speed, but it also means that you cannot easily switch. If you build a design around one part, you may be stuck with that one part from that one manufacturer. Again, this is changing slowly. There are also diminishing returns here. As you increase the switching frequency, you may shrink that transformer or inductor, but you may offset that by having to increase your EMI filter size. It may also be that your transformer costs more and runs hotter, but doesn't get smaller as the losses increase. That said, there are definitely other uses for GaN and SiC. You don't have to increase the switching frequency. You can use them to enable some of those diode bridgeless topologies that we talked about. And with silicon carbide in particular, it can be useful for simpler designs. Silicon carbide switches come in higher voltages, and that makes it easier to implement higher voltage for the 3-phase AC input and also higher voltage at the DC output. Better cooling, of course, is natural. As the power levels go up at a certain point, you tend to move around 1 kilowatt or so from passive cooling to fan cooling. Passive cooling is the simplest form of cooling. It's reliable, it's quiet. There's no moving parts, there's no extra energy spent. But the power density is going to be reduced by the amount of heatsink fin area that you need, and the mounting orientation is going to matter. You need a certain amount of space around that heatsink, and it needs to be facing particular ways to be able to shed heat through air rising through the fins. At about 1 kilowatt, you tend to add a fan. This reduces heatsink sizes, but it adds, now you have an added cost, you've got a noise, and in particular, you have a moving part. If your charger is sealed but your fan isn't sealed, you have a moving part that can fail in a dirty or a wet environment and may need to be replaced. If you get a sealed fan, you've added more to the cost. Somewhere around 6 kilowatts or so is the break point where liquid cooling tends to make more sense, although this is more application specific. Liquid cooling gives you the smallest size for the converter, but not necessarily the smallest size for the system, because you have all these external components, you know, pump, radiator, coolant reservoir, hoses, etc. So liquid cooling tends to make sense when you're installed on a vehicle that already has a liquid cooling system for the traction system or to cool the battery, where you're part of an existing onboard loop. So denser construction, which seems like an obvious goal. The idea here being to build up and to make use of the 3D space. There are different ways to do that. Typically, it means that you're going to be stacking circuit boards horizontally and vertically on top of each other, as you can see in this photo of a 10 kilowatt EV charger that I've opened up. There's some filter boards on the left and right. There's a power board in the middle. It has some perpendicular control boards, and what you can't see is that under that is what's called a IMS board, a integrated metal substrate, copper core board, which gives you better cooling, which is underneath. Much of this comes down to the devices that you use and how they're cooled, whether you use a power module, a IMS board, if you decide to use top side cooled devices rather than bottom side cooled, so they can connect directly to the heatsink rather than through a circuit board. But there are challenges with all of this. As you move these components closer together, they need to be shielded from each other, so there's no EMI crosstalk. Creepage and clearance in terms of the insulation pushes the components further apart. As you have vertical boards and multiple boards assembled together, they can be susceptible to shock and vibration, so that they need to be held in place, and can be more challenging to cool. And also putting it all together from an assembly point of view, have to be very careful with the design. So system integration. As I said, if you can't make the box smaller, maybe you can put more features in the box and delete the need for another external box and reduce system size and cost. So one example, which we're doing in some of our newer products, including our new 3.3 kilowatt charger, is a integrated DC-DC converter from the traction battery to an auxiliary battery. So for example, from a 48 volt traction battery to a 12 volt battery, you might in the past have used a small external converter. Well, now you can delete that. That's less space, cost, connectors, wiring can all be put into one. These can at least share a heatsink, because typically you're not having large loads on the auxiliary battery while you're charging. It's while you're driving around. And in some cases, you can also share the power electronics. We have a clever patented way of doing that, which we're using in the XB3300. And finally, if you can't fit a big enough charger on board, you may have to go back to the future and put it off board. So we've seen the chargers move from off board to on board, and now we're in some cases seeing them move off board again. Typically, you don't actually move off board. What you do is you have an onboard charger for the longer charges, and you also make use of an off-board DC fast charger when you really need speed. And sort of a gas station model of charging, particularly in applications where you're displacing diesel engines. The onboard charger can act as a communication gateway between the battery management system and the offboard charger. With the CCS, or the combo charge system, this is typically PLC power line comms over the control pilot. That's a sensitive RF signal. It needs to be carefully shielded and tuned, but you can integrate this function into the onboard charger with the higher level software protocols and stack that are needed to start and stop a charge session. So let's just close out by circling back to that charger that I showed, that Volkswagen charger, that a double power density. How did they do it? Mostly through denser construction. So there's no silicon carbide or GaN switches there, mostly through densely packed PCBAs, and then layers of shielding and insulation so that they can get close to each other without having crosstalk or shorting. They've coupled the devices and the magnetics very tightly to the coolant loop. It's quite an impressive jigsaw puzzle. It's not easy to assemble, and I would suggest that this design approach is reaching its limits, and it would not be possible to double power density again here without making some radical changes to the mechanical construction. So in terms of takeaways, I think we've covered a lot of ground here. Modern chargers have already come pretty far, but lithium-ion battery has changed everything. The battery is no longer the bottleneck, which means that the charger power and density has to keep increasing, and so it will. There are practical limits to AC power and DC current, and we've talked about how that needs to be solved by plugging in different places and increasing system voltages. There are diminishing returns with high frequency and with the new silicon carbide and GaN, although they will slowly make incremental changes, and they will start to be integrated into our future products. And finally, system integration can reduce system size and cost and add features and value. So that brings us to the end of the presentation. I think, do we have any questions, Paul?
Excellent. Thanks, Chris. We got just under 4 minutes to quickly get through these. There are at least 7 questions, but I'll start with the first one. What about non-lithium batteries moving forward, such as sodium-based batteries? Will chargers be able to charge other chemistries?
So we don't have much time, so I'll just go lightning round on this and say yes, absolutely. So sodium-ion batteries are going to make sense in some low-cost applications or stationary applications where you don't need a lot of power density, but you need low cost. From the charger's point of view, these batteries are going to be the same. Absolutely.
Okay. What charge rates do you normally see for lithium batteries, as in C rate?
Yeah, in the industrial markets that we serve, this is often a 2-hour rate or a 1-hour rate. In forklifts, for instance, where they're looking to replace 3 lead acid batteries that get swapped out, 1 for each shift in a 3-shift operation, charging at a 1-hour rate is enough that you can keep 1 lithium battery in 24/7 service by charging during breaks. So although there's a lot of talk about 5-minute, 10-minute charge times, that's not really what we're seeing today, at least not in the applications that we're serving.
Okay. Do DC power connectors provide limitations?
Yes, definitely. And this is particularly for the off-board DC fast charging. This is why they've started liquid cooling the cable and liquid cooling the connectors. In some applications, like even in golf, where the currents are low, because there's a lot of fertilizer present, and sea salts. If you're in a coastal region, you have to be concerned about corrosion of the contacts, and so these tend to be very oversized, and they look very closely at the platings to make sure that the resistance can't creep up over time, causing fires.
Okay. Can the XV3300 charge and provide the DC-DC for 12 volt?
Yes.
Okay. What is the design life for today's chargers? Do wide band gap devices affect this?
So I'm going to say that the wide band gap devices shouldn't affect the design life. At Delta Q, we typically design for chargers to meet or surpass the life of the machines that they're going into. So often they will serve the machine sometimes longer than the batteries in it. Certainly with lead acid, our chargers are reconfigurable so that they can be used with whatever the new batteries are, which are put into a machine when it's repowered. We go through a lot of validation testing, which takes months and dozens of samples, so that we can prove from a statistical basis and with a certain level of confidence that we will in fact meet the reliability that we're targeting and the life.
Okay. We have just 20 seconds left, so I think we're out of time, Chris. But thank you very much for presenting a great presentation, and thank you to everybody for tuning in. We had a good attendance for this session. If you do have any further questions for Chris, you can have a look at the chat, and you can reach him at the email address there. So thanks, everyone. Wishing you all the best, and have a great day. Take care. Thank you.
Okay, thank you, Paul.